Howdy, everybody. Hope you're doing well wherever, whenever you are. Um, Today was another fun day. Kind of interesting as I was debugging. It looked like they were having some networking issues or something like that. I mean, maybe it was my computer, but the site seemed to be down. I had fortunately already solved it, but it seemed to be down a little bit. So anyway, everybody codes Quest 2014. Nope. Quest 14 2025. Did I get it? It was a fun day. It's Conway's Game of Life plus cycle detection is, if you want the gist of it, that was at least the way that I solved it. So yeah, and I love your answers. I love your comments and stuff like that and your solutions. I've been looking at them, especially through the Reddit threads. Even after I do these videos, I still look for optimizations and things. For example, one had mentioned, I think I talked about it the previous day, it might be possible to calculate where in the index you are. Sorry, like where in the array you are without having to build it, if that makes sense. I also think you don't have to build the array. Like even you could chain the iterators and then just get the nth one based on the modulo operator, which might be interesting. Well, you could definitely do it for part 1 and 2. Part 3 would be interesting to do it that way, but anyway, we'll move on to Quest 14 and we'll talk more about those things in the recap. So lots of interesting stuff from everyone. So what is today's like general idea is you've unlocked the door and you've gone in the cave, and when you go in there, you're on a floor of tiles, and you notice the tiles are like lighting up kind of in different things, and what you actually notice is the way they light them up is a little bit equivalent to a Conway's Game of Life. And so that's where like part 1 comes in, is it says you're going to be given like a grid, and you're going to implement Conway's Game of Life, except for the rules are right here. If a tile is active, it remains active if the diagonal neighbors are odd. And then if a tile is inactive, it becomes active if the diagonal neighbors are even. Did I say that right? I think I did. So you're basically looking for active diagonals, and then that will tell you whether to keep something active or to turn something inactive to active. And that was it. And it said, run it for 10 rounds and see what you get. And the way you like see what you get is at each round, you count how many tiles are active, and then sum all of those up over the rounds. And so that was part 1, right? And so you do that for 10 rounds. So my code, this time I'm like, oh, do you know what? I'm going to try and use some structs. So maybe I overstruct this thing. The previous times I tried to do it more like how you do in competitive programming, where you just have the grid and you do row column stuff. I still do that a little bit here, but I thought, oh, I'll build a struct so we can see what that looks like. Anyway, so for parsing my input, I just can do grid from, and it's just write the lines and the cars of each line. I do a make new for part 3. Part 3 wants you to start with an empty one. But otherwise, the interesting parts are for the grid, you say, what is the next grid after mine? And if you've done Conway's Game of Life before, you just have to remember that like it's really hard to like update the state of the current grid. And it's much more easy, at least maybe for my feeble mind, to make a copy of the current grid and just look at the previous grid and say what are the diagonals and what should I change this one to. So that's all we do right here, right? We enumerate through the lines, we enumerate through each of the characters, and then we call this function that says how many diagonals are we. And then there's only 2 cases where it changes, right? They mentioned it. So if it's a hash and it's divisible by 2, is a multiple of 2. This is, I think I'd mentioned this before. Clippy will ask you to do this as opposed to modulo 2 equal 0. Anyway, if it's a hash and it is even, then it becomes a dot. If it's a dot and it's even, then it becomes a hash. I think is like the way that you can interpret the rules. Like that's what happens. Otherwise, it stays the same. So that's our next. And then we just have to determine the value. And it occurred to me, I think I've done this before, where like when I'm calculating these things, I do like an iter and then an iter within the iter for rows and columns. I had forgotten the flatten, and for some reason today it came to me. I think I was reading someone else's solution previous days, and it just popped in my head, oh, this is a great case for flatten, right? Because I can flatten all the iterators, and then I just say how many of them are hashes, and I get the count. You do have to do the double deref, but otherwise that's how you get the value. And then you ask yourself, okay, well, how do I get the diagonals? I mean, we've done this before over the last few days. Right. So in this case, it's not all the neighbors. We're just interested in the diagonals. So that's my 1, 1, 1, -1, -1, -1, and -1, -1. So what do I do is I go through them. I filter them by, is the neighboring row, in the grid? That's these parts right here. Am I still in the grid? And if I am I a hash? Is the diagonal a hash? So then I can just count those up, right? I say filter by this and then count them up, and that gives me the number of diagonals for calculating this. So what do you do for part 1? You actually do this for part 2 as well. You just go through all the rounds, and I thought it'd be cool to use a scan this time because you're just updating the grid. It turned out the scan not to be useful for part 3, but the idea is, you update the grid, right? So you update your state, and then you return the current grid's value, and then you can just sum all those values up. So yeah, that felt like cool. You could do a for loop, but I thought, I think this one will work with scan, so I tried it. I think it looks pretty readable, but again, you could do it as a for loop, right? And it would probably look about the same, and just have a total you sum over. That works too. Anyway, that's part 1. Part 2, probably the smallest part 2 we've seen. It doesn't even give you an example. It's literally just like, oh, great, you've done it. Now do it 2025 times. So, I mean, that's all it was. It was literally just, at the time, I just copy and pasted, but I've since, moved it into a simulate function. But now you do it for 2025. I mean, that's all there is to say about part 2. The time is a little bit longer, so you can tell the grid is substantially larger, right? You're doing more work to simulate it, so it may be I'll be interested to look at solutions to see how they sped up the simulations to get to this thing. I suppose, well, we'll talk about it later, but there might be another way to make it faster. Anyway, that's all there was to part 2. Nothing special. In part 3, you actually hit the orb and crazy stuff happens, or you get through the room because you figure it out, and it causes some orb that was managing it to explode. And what you're doing now is you're still doing the simulation, but your starting room is going to be a 34 by 34 empty grid, and that's how you're going to start the simulation. So you're going to say, I'm going to take a giant empty grid and then run simulate on it. Except what they say is, now I want you to simulate it 1 billion times. So you're going to simulate it 1 billion times. That's what you're doing, right? Just occurred to me, do I have my mic correct? Yeah, I do. Okay. Yeah, so you simulate it 1 billion times. Obviously, you say to yourself, oh, can I do a giant grid that's like twice the size 1 billion times? it's already taking me 13 milliseconds to do 2000. I mean, maybe you could, I don't know, but it screamed cycle detection to me, and so that's what I did. The one gotcha is while you're simulating, the way that you're counting the values and summing them up is your input is still one of these, but you're looking for the inner part of the grid to be equal to this input. That is, so you start out with a very empty grid, and then in round 125, the middle of the grid looks like this. And so you're saying, I'm going to go through the cycle a billion times and figure out how many, figure out what, only keep track or only count the all of the hashes when the center is equal to your given input. I hope that makes sense. So you're going to go through it a bunch of times, but only some rounds you're going to increment the totals, right? You're only going to increment the totals for some rounds. So the real hard part then is the simulation is not hard. You do have to like find this center. You have to say, oh, does the center match? And that code wasn't too hard. I have it up here. I put it up here in the code, or sorry, in the grid. I just say, hey, does the center match this thing? And you really just have to think about, oh, I just had to find where the center of the grid starts, and then I just like check, does that, does what I'm given lay over my current grid? So I calculate where the starting row and column like this, right? And I don't think I have it anymore, but I actually did some math. I was like if you think about it, it was like it's like 34 minus 8, which is 26 divided by 2. No, 26 divided by 2 equals 13. Like I figured it was 13. And so as I start, but how do I can just calculate this generically, and it turned out to be just the grid lane minus the center lane divided by 2. I probably should have known that to start off. Obviously that's what would put it in the center, but yeah, that's where the start position is. So then you just go through, you enumerate through all the values in the center, and you check if the grid has those values. So I use all here, right? Because I want all of my rows to be equal, and I want every value in that in each row to be equal. So you can see I use all here twice. Now that I think about it, I probably could flatten this one too, right? Where you have like a row, a character, and a value. Anyway, I probably could do that too and simplify it. That might be a, maybe I can add it as a to do. Because I think that might be able to be flattened. But yeah, that's what you do is so the first thing you need to do is determine if the center matches. And then the next thing you have to do is, for this thing now for part 3, is detect the cycle, right? So you imagine you're going to go through, maybe it might help to draw this. I didn't actually set up my drawing thing, but we can try it. Nope. I think this is where it is. Oh, look at that. It's even got my old picture. Can I clear it? Maybe just move. Okay. So if you think about like what you want to do is you have like these 1 billion rows, and each of these things have like a specific value, and you could, most of them were 0, some of them were sun, but they all have like some grid input, right? Think about like the hash of the current state of the grid. Eventually, I mean, you presume it's going to overlap. And I actually think the number was 4096. Like that's where you found like the overlap. It seemed like it was this number. Maybe that just has to do with the way like an empty grid permutes based on these things. But again, like the way to think about it is you're going to be like keeping all of the grids in a hash set, and eventually you're going to say, oh, I saw this one back here. So now you know there's a cycle. You know there's a cycle. So there's no need for you to calculate the rest of this. And this is not drawn very well because this goes on like substantially forever, right? The cycle size, again, is only like 4K, but you have to go 1 billion steps. So now you know what the cycle is. So this is the cycle. So now you can calculate the rest of this by just saying like, okay, well, here's like the pre-cycle part. I just need to add that value, and then I need to add my cycle times how many cycles left, like how many cycles are left, and then that will account for almost all of it. And then there's this little remainder that you need to calculate. So like those are like kind of the three things you need to calculate, and I'll show you those in the code. But again, we're doing a cycle detection, so we're looking for, oh, I've seen this state before. And once we've seen that state before, we now have a block of it that we can say this is going to repeat over and over again this many times, right? So it's like the pre plus the cycle times the number of cycles plus the remainder. Like that's what we're trying to calculate. I hope that makes sense. So again, I was kind of feeling, I don't know, feeling struct-y. So here's my cycle detector. I'll show you that in a second. But what part 3 does then is you create your empty grid, you create my cycle detector, the thing that I set up, and you just loop through the states, and you add those states to the cycle detector, and eventually it's going to say, oh, I found a cycle, here's the total. And that's what it is. The code isn't perfect. I thought, oh, maybe I can make this cycle detector kind of generic. And as I got about halfway through, I'm like, oh, this is kind of specific to the problem, because in some cycle problems, you don't want to like calculate a total. You want to like know the first value of the cycle and the second value of the cycle, and then to do some math on it or do some comparisons. Anyway, I still think I like my solution. I think it could be further improved, and maybe there's ways to make it more generic. But let's just talk about how the cycle works, right? Well, we want to keep anything we've seen, right? We want to keep all the states that we've seen before. That's obviously important because that's what's going to help us detect when we've seen a cycle. And then we want to keep, it's called a prefix sum. I talked about this in a couple previous videos very briefly. It's just like keeping a running total, right? So like the idea is, will I be able to get there? The idea is if we know this value was 0 and this value was 1 and the next value was 5, we're actually going to put 6 here because it's the sum of the previous. And then we know this one's 9, or we set this one to 9 because it's like, say it's 3. And so it's 6 plus 3 is 9. And then we know when this one is 56, or what, say we know this one is 56. We now know the total of the cycle is 56 minus 9, right? 47. So that's the cycle total, and now we can multiply that by how many cycles we have. That's what I think it's helpful to, at least in my mind, I was like, oh, I should use a prefix sum here because then I know exactly what the values are around it. And then we just keep track of the total rounds, right? The total rounds that they want us to run, because we can use that to do the math. So what do we do when we like make a step in our cycle detection? We add our round, I wonder if someone's already implemented a cycle detector now that I think about it. How to add that as a to-do. Cycle detection comes up a lot, so maybe knowing a generic cycle detection algorithm is helpful. Again, the idea, though, I think is probably, if you've done these puzzles, pretty familiar. You basically are just tracking what you've seen, and now you know the cycle. Anyway, so what do we do first? We update our state, right? So we update our prefix sum list, and we update or we track our current round. This is just a helper because I think we use it in a bunch of places. Yeah, you can see we use it all over the place. But what do we do? How do we detect the cycle? Well, if a cool thing, I remember we've worked with hash sets before, and it will tell you if it's already seen the value. Hash maps will also do that as well. So when you do an insert on a hash map, it will tell you, or it will return the previous value. And so what we do is we just say, hey, if we have a previous value when we do our insert, we now know that we have detected a cycle. And so we know the cycle starts at the previous value and it ends at our current round. So we now can detect the length of the cycle, which is round minus start. We can detect how much we have left to do, right? I did this a little bit differently, but you could potentially, I mean, you could do this other ways, I guess, but I said, how much do we have left to do? And then how much is the sum of the cycle itself? So again, because we've done a prefix sum, it's just the sum of the current round minus the sum at the start, which was this, like I'm talking about right here, what we were doing right here and right here. Because we know this one's 56 and this one's 9, we know the cycle is this side. And then the remaining, I guess, this is the remaining right here, is like from here to here is what we're calculating, if that makes sense. So now how do we calculate it? Is we say, oh well, it's the prefix sum for the current round. So that gets us, maybe I'll do that different color up here. So we're now going to calculate, we're going to have this value, so the previous plus the remaining divided by the length of the cycle. That's going to tell us how many cycles are in the rest of the list, and times that by the sum. So that's going to get us this value right here. Like the cycle values. That's going to get us this. And so now we just have to do this remainder part. And that is this right here, which is take the start and go from, or sorry, I should say, take the difference of the start plus the remaining divided the remainder, that the modulo of the remaining, and subtract that from the start. This actually, when I did it originally, I was defaulting to like 0 if they were the same, but I realized if they're actually the same, if there is no remainder, it is 0. And so it would just be start minus start. And so I did simplify that a little bit. There might be further ways to simplify this, but again, the gist is you're subtracting this minus the start. That gives you like how much you have remaining to push in. Okay. Again, I was trying to be generic. I think originally I had unreachable here, right? Obviously, eventually, I presumed we would find a cycle. But technically, if you don't find a cycle, you could just do this. You just say, hey, have I exceeded my rounds? If so, just give me the last prefix sum. That means I've like gotten to the end. I've gotten through all 1 billion. And so here's the result of going through all 1 billion. is basically what this does. But I put it unreachable. I did this because when I was updating the code and kind of refining it for display for the video, I thought, oh, maybe this will be reusable. And I don't know if it will be, but obviously you want to handle this case if the cycle, like if there is no cycle, and so it goes forever. So that's why that's there. But again, I hope you understand, like, the general idea of cycle detection is go through your states and keep track of them. And once you find a state you've seen before, you now can use the start and that end state to get the value of each cycle. And then you just times it by how many cycles you have left. And then you really just have to account for this little pre part and the little remainder part. That's something that you always had to do. I think when I was testing my original solution, I forgot the remainder. And I was like, oh, and that's just something you have to remember, right? Is you have to say, oh shoot, you have to account for the remainder because the cycle may not get everything, right? Is probably the best way to think about it. So you just have to make sure to handle that thing. If you're like me, you've done it before. It was this part that I had forgotten, right? I forgot this remainder. So my numbers were just like a little bit off. Depending on how you do it too, I noticed that I had I kept track of like the sum up to the current round, and so I had this remaining. So I'm not quite technically doing it the way this top shows. I'm more doing it like this orange shows down here. You could do it either way though, and I think either way would work just the same, especially if you're doing a prefix sum, because it's really just math and indexes and arrays. So however you decide to do it, it's not going to take long. At least I don't think so. So anyway, that's part 3. I thought it was fun. We've done cycle detections before, and we've also done Conway's Game of Life before. So I do feel like it's having done these and getting the reps in has actually helped me, because I think the first time I did cycle detection, I really struggled, and I've now probably done it, I don't know, 4 or 5 times now, and I feel like it's getting better. So if you're new and you're having issues, you feel like the cycle detection is really struggling, it didn't work for you, I'm happy to help debug your code, or just know you got to get the reps in, and that'll do it. After you've done it 3 or 4 times, it's the same thing. So like if I was going in to an interview and someone's like, how do you rebalance a red-black tree? I'd be like, brr. I mean, I haven't done that in like 25 years, right? So I just don't I don't remember how to do it. I'm sure given enough time and reading Wikipedia enough, I could figure it out again. But it's just like anything. Cycle detection is like a huge thing in programming puzzles, and so if you like programming puzzles, it's probably something to put in your thing. In fact, I haven't even looked, but like competitive programming cycle detection, I wonder if there's like a general aggregate. Oh, I have seen some of these, but these are more like state graph type things. Anyway, you see, I don't think I saw my birdie today. We're definitely getting bigger. But just occurs to me we're almost done. 1, 2, 3, 4, 5, 6. We just have tomorrow and next week. Oh, but I'm looking built, bro. Look at me, bro. I think I did pretty well today. $43 minutes. Okay. I feel like I actually do better when I'm not live recording my videos, and I think it's because when I'm live recording, I like to like think through my thoughts and like try and speak them out loud. Whereas if I'm just programming, I can put on some music that makes me type faster and go to town. Yeah, the video would probably have been a couple hours if I had solved this one. I suspect. So not as good as yesterday. Oh, but I actually did get a better place, 44th place today. Interesting. Interesting. What was yesterday's? Oh, it was just modulo stuff, right? Oh, and building the clock. Maybe that's not as hard as the cycle detection. Yeah. Anyway, it was a fun day. I had a lot of fun doing it. Should we see how other people solved it? Pretty much implemented the problem statement for the simulation plus cycle detection. I'm a big fan of the O1 space step function and the bit mask trickery used for the pattern check. Ooh, that's true. I used vec-vec-car. You can do bitwise operators. I don't know why I didn't do that this time, because like the last few days we've talked about it and found solutions that use it to like greatly speed their times up. Step total active. Yep. Okay, yeah, that's what I did for the first two parts. Well, where's the step code? Floor load. Oh, there must be some module in here. Floor. You can do it as a byte value too. Okay, yeah, they're using a bit mask. Like, I don't want to give away all the fun. Oops, what did I change here? I think I did this for part 13. Is that the one it was? No. 12? Yeah. I did turn it in. I did do a bit mask instead of. I was using a hash map to like store the barrels that I blew up. And I tried a vec bool as well, but a bit mask was the fastest. So if you remember, you were tracking like the barrels you blew up, and so I did implement a bit mask. The thing is like in that one there were enough of them that you couldn't do it in a single one, and I suspect that's the case here, right? Is like they probably in their, what is their floor? Yeah, it's an array of things. Interesting. Very cool. Okay. Bitwise simulation plus cycle detection. Okay, let's see what we got here. Okay, you treat each row as a U64. Yeah. And just whether each one is turned on or not. Okay, sounds like the same thing here. It's crazy that this works. I don't even have the mind power to grok this right now. I may have to wait for a minute. Yeah, but it probably makes it faster because yeah, now look, you just have like an empty grid. You're not like stowing around. It's just a bunch of zeros as opposed to I'm creating a new character, a character grid each time. So this would definitely speed it up. The problem is like in the time that you're doing it, you have to think about like this kind of thing, right? Like how do you iterate over these? Uh, it's probably easier after the fact. At least for me, it would be to like turn it into a bit mask. Looks like they just keep the matches in a vec. It looks like the math is pretty close, although you have to do some additional calculating. I think this is where you might be able to, if you do prefix sums, you can like do some stuff. I presume just because they use the vec bit mask, it's really fast. And this for loop is probably not too crazy, but like you could imagine that if you're keeping a prefix sum, you try. This might be faster, although the act of keeping the prefix sum may have some cost to it that may make this actually faster in the end, but the logic itself is largely the same. I think was what I would say. uh, uh, uh. Okay. Yeah, if you're very specific for this input, it's pretty easy for you to like determine if the center is a pattern. I kind of went with a generic approach. The trick is to see that there's a loop. Yep, perfect. Okay. Nothing super interesting. I think again a bit mask would be interesting. An interesting update. Sorry, you probably can't read these. I did again. The cycle length is, I think I put 4096 or something like that. It was something like that. Yeah, that was a cool thing. When I hit that, I'm like, oh, because if you know the period, it's going to be the same, presumably, for everyone. So that is true. You could probably calculate it pretty easily. And then just for each thing, for part 3, you just have to track what your total is in the cycle, and then you could get your sum. Okay, yeah, very good. Yeah, it never cycles back to the 0th round, the original input. I actually looked at first. I'm like, oh, does it ever go back to an empty slate? And it doesn't. It just cycles back to the first one. But I'd already implemented the generic solution. This was something interesting. Is like you can get back to the first round or like the very first round. So I think in my drawing, like this previous part, doesn't actually exist because you actually find the cycle like right here. Excuse me. But it's good to calculate that anyway, or just to know about it when you're doing cycle detections, because sometimes the cycle doesn't start at the beginning. Like we've done, I think it was just last year, there was an advent to code where you had to do cycle detection, and it was like, somewhere well into the middle. So, okay, very good. Nothing, again, I don't think there was anything too crazy in the solution so far, but I will look. I'll look at your solutions too. And let's see. We could add a to-do here. Maybe we could try, for the recap, I'll try implementing it as a big bit mask, see what that looks like. Because that might be interesting too, but I'm pretty happy. I think most of the time, if you can get your solutions less than 100 milliseconds, especially for these bigger ones where you're doing like cycle detection, I think you could feel pretty confident about that. So, yeah, just keep plugging away. I'm having fun. It's kind of sad to think that we'll be done, although, you know, it won't be too long after it finishes. Is that right? Let me look at the calendar. Yeah, we'll finish on the 28th, and then Advent to Code just starts a few days later, that next Monday. So it'll work out perfect. We'll go right into Advent to Code, and that'll be fun. I think it's been a fun story too. So this is one of the reasons why I like doing Advent to Code, and also Everybody Codes, is I like actually think following a story is interesting, you know. So I've always been more into like video games where the story is immersive. It's not just all like, can I click pixels faster than everyone else? I mean, I do play some of those games sometimes, but it's like, can you get into the story? And I definitely think, you know, Advent to Code and Everybody Code so far has had some good stories. So there you go. Send me your solutions. Let me know what you got. Otherwise, we'll talk to you next time. Thanks, everybody. Bye.